Science never ends. Welcome to the series of videos about Nobel Prize winners, a group of interesting and inspiring scientists. Have you ever heard of a woman whose husband, daughters, and son-in-law were all awarded the Nobel Prize? As for herself, she is the first woman to win the Nobel Prize and awarded Nobel Prizes in 2 scientific categories. This video will take you into the life of this great woman, Marie Curie. Marie Curie was born in Warsaw, Poland, on November 7, 1867. Marie was a brilliant child, with a great gift for languages and an extraordinary memory. She graduated at the age of 15, and she was first in her graduating class and received many academic awards. Marie began to work as a private tutor because no universities in Warsaw admitted women at that time. It was during this time that Marie, for the first time, had the opportunity to perform laboratory research. Her cousin had returned to Warsaw after studying in Russia with Mendeleev to direct the museum at the Ministry of Industry and Agriculture. Under his tutelage, Marie secretly began to study chemistry, performing experiments in the chemistry laboratory that formed part of the museum collection. During this period, Marie discovered her love of and talent for experimental laboratory research. In 1891, Marie went to Paris and enrolled at the Sorbonne. In 1893, when Marie received her licence de sciences, equivalent to a Master of Science, she was one of only 2 women recipients at the university. On July 26, 1895, Pierre and Marie were married in Paris. This couple would perform research on magnetism as a team for the rest of their lives. And, more amazingly, this family would have 5 members to be awarded the Nobel Prize in the future. In early 1896, only a few months after X-rays were discovered, Henri Becquerel reported to the French Academy of Sciences that uranium compounds emit rays that can fog a photographic plate. However, the weaker Becquerel rays, or uranium rays, were neglected by the scientific community. The ignored uranium rays appealed to Marie Curie. Through numerous experiments, Marie confirmed Becquerel's observations that the electrical effects of uranium rays are constant, occurring regardless of whether the uranium was solid or pulverized, pure or in a compound, wet or dry, or exposed to light or heat. She went beyond Becquerel's work, informing a crucial hypothesis. The emission of rays by uranium compounds could be an atomic property of the element uranium, something built into the very structure of its atoms. Marie tested all the known elements to determine if other elements or minerals could cause air to conduct electricity better. In April 1898, her research revealed that thorium compounds, like those of uranium, emit Becquerel rays. To describe the behavior of uranium and thorium, she coined the term radioactivity. She found that 2 uranium ores, pitchblende and chalcolite, were much more radioactive than pure uranium itself. She concluded that the highly radioactive nature of these ores might be due to one or more additional, as yet undiscovered, radioactive elements. Pitchblende is a highly complex mineral, comprising combinations of up to 30 different elements. After its isolation, it was eventually discovered that 2 fractions, one containing mostly bismuth and the other containing mostly barium, were strongly radioactive. In July 1898, the Curies published their conclusion: the bismuth fraction contains a new element. Chemically, it acted almost exactly like bismuth, but since it was radioactive, it had to be something new. They named it polonium. A second publication, in December 1898, explained their discovery in the barium fraction of another new element, which they named radium. While the chemical properties of the 2 new elements were completely dissimilar, they both had strong radioactivity. To convince the scientific community of the existence of polonium and radium in addition to completing the identification and establishing the nature of the new elements, Marie set out to isolate them from the bismuth and barium with which they were mixed. Despite the Curie's industrial assistance, it took Marie over 3 years to isolate 1/10 of a gram of pure radium chloride. For her research on irradiation phenomena, Curie became, in 1903, the first woman to receive a Nobel Prize. In 1911, she was awarded another Nobel Prize for the isolation of radium, this time in chemistry. She is the first recipient to be awarded Nobel Prizes in 2 scientific categories. Polonium is a rare and highly radioactive element that has no stable isotope. It is a silvery gray, radioactive semi-metal found in uranium ores that is chemically similar to the elements bismuth and tellurium. Polonium is an alpha emitter and, hence, is used in anti-static devices and for research purposes. It is used in the form of a thin film on a stainless steel disc as an alpha particle source. It is used to eliminate static electricity produced during processes such as rolling paper, wire, and sheet metal. Due to its alpha emission, 1 gram of polonium can acquire a temperature of 500 degrees Celsius. This property of polonium makes it a useful source of heat for space equipment. It is used as a source of neutrons by mixing or alloying with beryllium. Polonium-210 is used as an atomic heat source. The only disadvantage is the isotope's short half-life, that is 138.4 days. The main field of application of polonium-210 is the manufacture of atomic batteries used in spacecraft. Its lifetime allows polonium to be used as a source of energy in atomic batteries of spaceships. Only 7.5 gram of polonium is enough to obtain 1 kilowatt of power. In this respect, it is superior to other compact atomic energy sources, for example, as fuel for the stove installed on the Lunokhod 2 rover, maintaining an acceptable temperature in the instrument compartment of this apparatus. Besides, polonium is irreplaceable in nuclear physics. It is widely used to study the effect of alpha radiation on other substances. The chemistry of radium is analogous to barium, which is commonly used as a surrogate due to the intense radiation of radium. Radium metal is soft and lustrous and silver-white in color, but it is never found in nature as a pure metal, as it is highly reactive and rapidly reacts with nitrogen in the air to form a black layer of radium nitride. The alpha rays emanating from radium would become an amazing tool in the exploration of the microscopic structure of matter, leading to the discovery of the atomic nucleus. The relative natural abundances, differences in parent and daughter chemistries, and the distinctly varied decay characteristics of the naturally occurring radium isotopes make them useful for evaluating natural phenomena such as volcanic rock formation and groundwater exchange with surface water. Short-lived, alpha-emitting radionuclides, such as 223-224 radium, have great potential for use in therapeutic radiopharmaceuticals. Alpha particles are highly energetic, relatively large, and have a high charge-to-mass ratio, which allows them to readily interact with surrounding matter and frequently create ionization events along their path. The effectiveness and small, targeted deposition range make alpha particle therapy an exciting alternative to other radiotherapies. In 2013, 223Ra radium chloride became the first and only alpha-emitting radiopharmaceutical to receive FDA and EMEA approval for clinical use, with the intended purpose to treat metastases associated with castration-resistant prostate cancer. Starting in 1948, 224Ra radium chloride was used to treat ankylosing spondylitis in Germany. He was a pivotal figure in the golden age of microbiology. He discovered the bacteria that causes anthrax, septicemia, tuberculosis, and cholera, and his methods have enabled others to identify many more important pathogens. He is known as the father of bacteriology. Do you know who he is?